this is our data project. I'm Joseph Till, and the other people in this group are Macy and Eli. Here's our splash page, just giving a little bit of background about who we are as a group and what our project is about. Here's a couple of useful links, the Kaggle dataset, and then also a link to our clean dataset. In this little part, I'm going to just mainly go over the research abstract, and I'm going to start by just noticing that this is a border crossing dataset about all crossings into the U.S. border and all those recorded incidents between the years 1996 and 2020. For our modeling, though, we're going to specifically focus on the years 1996 to 2019 because 2020, as shown in this graph, is very low in terms of data amount compared to the other years. We're also, with our model, just going to focus on bus passengers, personal passengers, and pedestrians. This is because we'll talk about this later, but this is just allows us to look at the types of people that are actually crossing the border and look at the predictors for them individually. The other thing that we're going to do is, based on the predictor, we're going to look at the year, month, state, and border variables. Those are the main variables we're going to analyze for predictions, but also note that in the original data set, month and year are part of the date variable, and we clean that out, and we'll explain that later. The other thing I want to talk about briefly is with all of our models here, which are all here, we'll explain each of these later, is that we are only looking at the amounts that are greater than 10, and this is due because there's a lot of amounts of 0, and we just want to look for more significant amounts, so it's easier to find actual predictors for them.
Alright, when it comes to cleaning the variables port name, port code, and state, the first thing we did was we trimmed any of the leading or trailing spaces within the observations, and then we used an as factor command to change port code, port name, and state to factors, because we don't want R to recognize these as just regular categorical variables, but factors, because they're each a specific group. The next thing we did was we checked to see how many unique port codes there were and how many unique port names there were, because theoretically there should be the same amount with one port name having one port code. But we found that there were 117 port codes and 116 port names. So we saw that there was an east port in Idaho and an east port in Maine. So we just added the state abbreviation to each of these so we can decipher between these two, and then we found that there were the equal amount of port names to port codes.
So I was in charge of cleaning out the border and the date variable. So the border, these two graphs here are just looking to see the counts of them and to see if there's any weird spelling mistakes, which there are none. Finally, this we separated just to make the border read Canada and Mexico, as shown here below, checking to make sure again that there's no spelling errors, which there are none, successfully cleaning out this variable. The second one that was kind of more of a hassle was cleaning out the date, because we had it in a format of month, day, and year with separating by the backslash. So we decided to keep the month and the year, so we separated them out and just took the day, and that allowed us to have a month and a year, and we organized the month to run in chronological order from January to December. And then we just looked to make sure there's no spelling errors and that everything looked good and that there's a fair amount of data for each month, which there is, so everything looks good there. And then we also just checked year to make sure there's no spelling errors, and which there is none. And then that is it for cleaning this little portion of the data set.
I worked with the measure variable and the value variable and cleaning them. So here at the bottom it kind of explains what I did. So for the measure variable, I changed the name because the variable kind of shows the number of, or the different modes of transportation that people use to cross the border. And we just felt the name didn't fit very well and it was a little bit misleading. So we changed the name to transportation to kind of represent the data better. And the second change we made to that was shortening the names of all the data under the transportation variable. The names of all the vehicles were kind of long, and having those in the graphs and models that we made later would have made it very hard to read because they'd all overlap and just make it confusing. So we shortened them to make it easier on us and whoever else sees it. For the value variable, we did not make any changes to it because it's a very cut and dry variable, and it just shows the number of people going across the border, so there was nothing that needed to be changed there. After cleaning my data and combining it with the other cleaned variables from the rest of my group, we used the completed clean data set to create the classification and regression tree models and the random forest models to follow our research abstract model to see which variables were the best predictors for each of the individual forms of transportation that we found. The individual forms that we used were bus passenger, personal vehicle passenger, and pedestrian.
Now we're going to be looking at the cart and random forest model for bus passengers. But before all that, the first thing we did with bus passengers was look at the distribution of the values. And as you can see here, it's highly skewed right. So in order to mitigate that, we got rid of all of the values from 0 to 10, and we also took the log of value. Here's the distribution after taking the log of value and getting rid of the values from 0 to 10. The next thing we did was try and find the best value for the complexity parameter for our trees. And as you can see here is a plot of some complexity parameters, and as the CP value goes down, so does the error. But as you can see, the cross-validated error is not going down too much from here, maybe 100th. So we decided that 0.001 would be a good complexity parameter. So with that complexity parameter, we made a tree, and as you can see, state is likely the most important variable here, having the first few splits. We also see that year is important, and that month also has some meaningful splits over here. Notice that border is not on this tree. Here's another visualization of that same tree, and after we made these trees, we made the random forest model. Here's the variable importance plot for that random forest model, and here we can see that state is by far the most important variable for bus passengers, followed by border. Also note that border is a less important variable when predicting the bus passenger traffic when compared to pedestrian and personal vehicle. Also, here we can see that year and month are the least important variables in predicting bus passenger traffic.
So I look specifically at the pedestrian models for this data set. The first thing to point out, again, is taking the values greater than 10. The rationale for this is described earlier in the research abstract proposal of this video. The other thing to point out is we saved the state, month, and border as factors, and this is for to be better used in a cart model. This is taking a graph look at the year, and like we've talked about, we're going to take out 2020 because the amount of data for that year is so much lower than all the other years. The other thing that we noticed is that for all of these, and for mine specifically, is that the counts of the amounts of pedestrian values are substantially right skewed, so we took the log value of it. While this does not yield a normal distribution here in this graph, it is a lot easier to work with, and it shows that it's a lot better than having a significant right skew. Then after this, I looked at cart models for all of our potential predictors, which are month, year, border, and state, and I looked at all of them individually. Month and year both did not yield a cart model. We got one split for Canada with the border, and we got a couple splits with state, which to me is, and then these are just the PRP versions of those R-part cart models. And then I kind of concluded that it seems that state and border tend to be the better predictors. And then I looked at just a general cart model with a very low CP just to see all the different types of predictors and root nodes and splits I would get. And it seems that state take up the majority of the main splits. After that, I kind of tuned this a little bit and then looked at the best CP, which turned out to be 0.0012, which yielded this model. And that shows again that states take up the majority of the first splits. And then following that, I just took a random forest, and then I looked at a variable importance plot, which determined again that state and border were the best predictors for the value of pedestrian. This just all kind of goes to show that state and border are better, and it really helps to explain the amount of pedestrian crossings.
I'll be looking at my personal vehicle passenger model with this link, which will take you to this page and just kind of shows you everything I did working with these models. So first I started here by filtering out all of the zeros from the value variable, just because we don't want those values to skew the data at all. Since they're just zeros, they're not that important. Next, I made graphs for each of the predictors that we were all working with, which were border, state, year, and month. We wanted to see which predictors would work best with our forms of transportation. So this is our random forest with all of the predictors together, and then we have it split individually by month, year, border, and state. So as you can see here with the random forest models, the state and border seem to have the biggest reaction and biggest results. And then we did the same thing with the cart models, where we started with all of them together and then separated it by month, year, border, and state, and again we get the same thing as the random forest models. So then after that we tuned those models and created importance plots to see which of our 4 variables will work best. And looking at the final importance plot, we see that state has the biggest influence, with border as a second, and then month and year don't really influence it at all. So we can conclude for the personal vehicle passenger that the state and the border are the best predictors.
Now for our conclusions. Based on our findings from the data, we can conclude a few things. The first of which is that the variables don't predict pedestrian, personal vehicle, and bus passenger traffic in the same way, but the most important variables between them are the same. According to our cart models, the first 2 to 3 splits for all 3 cart models, being bus, pedestrian, and personal vehicles, had to do with the state that the border crossing occurred in. Similarly, based on our random forest model variable importance plot for bus, personal vehicle, and pedestrians, the most important variable in predicting each respective form of transportation was state. This is likely because some states' ports are more relevant than others in terms of how many border crossings occur there, which could be due to the geography of the state, which cities are near the ports, and many other reasons. Interestingly, while border was the second most important variable with all 3 modes of transportation, it wasn't included in any of the cart tree splits. This is likely because the state variable does everything that the border variable does, but just in a more specific and in-depth way. So while border is a good predictor of the number of border crossings, having the state variable effectively removes the need for the border variable. Year and month were also relatively less strong predictors for all 3 modes of transport, but played a more significant roles in cart trees for bus passengers. One plausible reason for this comes down to the fact that bus tours are more likely to occur in warmer parts of the year across the country, especially in the north, making bus passenger traffic more dependent on the month. Overall, when predicting the amount of people crossing a border, the most important variable to consider is state. Secondly is border at which it occurred, but as said before, the state effectively tells which border the crossing occurred at and the state as well. Also note that the border variable was more significant for personal vehicle and pedestrian traffic. Lastly, year than month were respectively the 3rd and 4th best predictors, both of them being much less significant predictors when compared to border and state.